So the homework, you had this wall, 15 centimeter and 8 centimeter high. So obviously this is not to scale. And the surface is hot and it's surrounded by air at 20. And he would like to cool it. So how can he cool that thing? Well, he would going to put fans on it. Bunch of them. That's the spacing between the fan. That's the height of the fan. That's L over here. Alright. So the fans are 0.1 centimeter thick. So that's the thickness T is 0.1 centimeter. And they are 4 centimeter wide. So again, this is not to scale really. 4 centimeter wide and 18 centimeter long in the vertical direction. Right? So this is 8 centimeters. So again, this is not the scale. This is supposed to be 4 and this is supposed to be 18. Right? Notice that the height in the vertical direction is what's really important for us. Because the boundary layer that will end up forming, thermal boundary layer that will form on this plate will depend on how high it is. Right? The width or this 4 centimeter is not that important. It's important for the area, of course, but it's not important for the Nusselt number. All right. So he assumed that the pace is at 85. So of course you remember from the chapter 3 when we were dealing with fans, we know that the farther away you get from the wall, the lower the temperature would be, right? But if the conduction of this material is really big and the edge is really small, probably the conduction will be able to catch up and he can maintain the whole thing at the base temperature. So it's not that horrible approximation, especially if it's not really, if the fan is not really that long and if the material is such that K is really high and H is really small, then don't kill yourself over that assumption. That's okay to assume that the whole thing is at 85 degrees C. All right? So what's required? The optimum spacing and the rate of heat transfer by natural convection and Q dot. So they are not, they are just looking at the ceiling now. Okay. So how can I get my my optimum spacing? There is this optimum Nusselt number, remember? And that optimum Nusselt number will have an optimum spacing corresponding to it. So that optimum spacing was such that the Nusselt number is 2714, and that make the S is 2.714 multiplied by L over the Rayleigh to power 1 over 4. And so to get the Rayleigh number, you need to get the Kirchhoff number multiplied by the Prandtl. And to get all those guys, you need a temperature to obtain them, right? All those properties. What temperature should we use? T film. So T film, that's Ts plus T infinity over 2, right? And so how much was that? That was 52.5. And so then you can get the K 0.027, the Prandtl 0.72, and the nu 1.8 10⁻⁵ meter square per second. or basically you can get the Rayleigh number equal to 248 10 to power 7, and from that you can get the optimum S as 6.9 millimeter. Right? So coming up with that Rayleigh number equation, you get 2, and getting the S, the equation for the S, you get 2 points. So that's the optimum spacing. All right. So now how can I get my Q? A. You want to say HA, right? Yeah. HA, and let's figure how you can get the A in a second. So HA multiplied by, which is TS minus T infinity. So this is that. This equation is probably worth 30% in every problem, convection-wise. You know, just write that Q is HA delta T. H times the surface area times the delta T, the surface minus the fluid. All right? So Brandon is correct. So Q dot is HA TS minus T infinity. All right? So now we have to figure the H and we have to figure the area. So let's figure the H first. How can I get my H?
Nusselt number.
Nusselt number, exactly. So the Nusselt number, which is 1.307, will end up being H S over K, and so from that you can get the H as 5.2 watt per meter square degree C. And now the area. Let's get the area. So what is the area? So to be super accurate, the area is the base plus the surface, both sides, right? That would be the accurate way. The approximate way is basically to say that, and this is what he did in that solution. So he basically say the area S is simply just L times H, that's the area of the fin, multiply by 2, multiply by how many of them per this 15 centimeter. So how many of them we will fit? How many fins can fit in this 15 centimeter? 15 divided by 15 divided by what?
Thickness
Plus
S.
plus the spacing, right? So Mary is saying to find out whether you are going to have 10 of them or 5 or 1, divide this 15 over the space that each one of them occupy. We occupy S plus the T, right? Each one of them. So it's the 15 divided by S plus T, right? And so you get, and in that solution he even, you don't have to do this, but he even say, let's just make it 15 over the S. Right, so why he did this? Right, because the S is 6 or 7 millimeter and the thickness is 1 millimeter. But this is actually the accurate way, right, really, but this is approximation. So he end up with whatever, 22 fin. This will end up with 22 fin. This will end up with 19 fin.
Are we supposed to round up or down? Yeah, that's a good question.
Let's answer that question one more time. So Brandon is saying, so which one of this is accurate, right? So this 15 over S plus T will end up being 19. Only 19 can fit if you take into account that it's not just the 7 millimeter, it's the 1 millimeter thickness too. You cannot fit more than 19. If you neglect the thickness, you will end up with 22. You can fit more. So what will happen in real life? 19 or 15? Oh, sorry, 19 or 22?
But if you get like 18 point something, like 18.5, should you round up to 19 or should you round down to 18?
No, it's 18.
That's
Are you going to be able to fit 19?
No.
Right.
Yeah, so I use 18 instead of 19.
Because what is the number? How much? Ah, it's 18.9. But come on, it's 18.9. I mean, come on, it's. I mean, you can squeeze it. I mean, seriously, that last one, you know, you can just push it.
Right on the edge.
Right. Let's really imagine you are really fitting this. Okay, I mean, you calculated the optimum, and the optimum is 6.9. All right, and so you do the 15 over S plus T, and you end up with 18.9. Right? No, you are the actual engineer supposed to make this thing cool down. What are you going to do?
Make the moments.
The last one, you have to squeeze the last one so that you can fit 19, right? Will you be fit? Are you going to go for 22?
No.
No, because you realize that if you add more, you will end up squeezing them tighter, and then the Nusselt number will drop. The heat transfer will not be as good. And you know that that's the optimum Nusselt number that we need to be very close to it to maximize our heat transfer. All right? So having said that, in the exam, I expect you to go with 18.
Okay.
Of course. But in practice,
Even if it's 18.9?
right. I expect you to say, well, let's go for 18, but you can write the comment that, you know, I would actually risk having my Nusselt number drop because it will drop in this last fin or the last pair when you squeeze them. You would say, I would risk losing my Nusselt number a little bit in the last part to get one more fin. That's a bigger area, right? So mathematically, what you did was right. You'd say 18. But practically, you will say, no, I'm not going to go for the optimum Nusselt number because I'm going for actually more bigger area. To optimize my design.
The heat transfer rate is bigger if you use 19.
So by adding another fin, you actually make it more efficient because you have another fin.
By adding, say that again.
So by adding another fin, you actually make it more optimal because you get more transfer because you have more area.
You will make the Q higher, but each one of those fins are not optimized.
Right.
Right.
So you have a kind of you have to figure out which one would be better.
So if you are going for the competition of the best efficient, for the highest Q, you would go for the more fins. But if you are going for the competition for what is the Q per unit area, for example, you would go for the optimum spacing. Right? So anyway, so you should go for 19. And so, how much is the Q? What did you guys get? The Q was 92.5 watt. Okay? Did you get 92.5?
Well, we used 18, so
So how much?
it was 80 something.
See? That's the proof that if we squeeze one more fin. But of course, we squeeze the fin and the H didn't really drop, really, in our calculation, right? Because I still use the same H. I shouldn't.
Somehow I ended up with
Right, and how much?
6.6, so it ended up changing a little bit.
Maybe the property was a little bit different. But also note that in that solution, and I think that's the solution we used in the example also, he's neglecting the base area, right? But in real life, the base is also convecting. The air is sitting there and is convecting from everywhere, not just the base. So that's another approximation. Did anyone take the base into account? No one? All right.